Welcome back to this next installment on artificial intelligence and deep learning. In today's video, we will talk about deep learning. Deep learning is a subfield of machine learning that involves training artificial neural networks with multiple layers to learn patterns and relationships in data. The term deep refers to the fact that these neural networks typically have many layers, which allows them to model complex relationships between inputs and outputs. In deep learning, the neural networks is typically trained using large amounts of data and optimization algorithms such as stochastic gradient descent to adjust the weights of the network's connections between layers. By iteratively adjusting the weights, the network learns to recognize patterns in the data and make accurate predictions or classifications. Deep learning has been applied to a wide range of fields, including computer vision, natural language processing, speech recognition, and robotics. Some notable examples of deep learning applications include image and speech recognition, self-driving cars, and language translation. Deep learning has also seen significant advancements in recent years with the development of new techniques such as convolutional neural networks, recurrent neural networks, and generative adversarial networks, among others. These techniques have enabled deep learning models to achieve state-of-the-art performance on a wide range of tasks. Neural networks are a type of machine learning algorithm that is modeled after the structure of the human brain. They are composed of interconnected nodes called neurons, which work together to solve complex problems. Neural networks are capable of learning from large amounts of data and improving their performance over time through a process called training. The basic building block of a neural network is the neuron, which takes in one or more inputs, performs a mathematical operation on those inputs, and produces an output. Neurons are organized into layers, with each layer performing a different type of processing on the input data. The output from one layer is fed as input to the next layer until the final layer produces the output on the network. Training a neural network involves adjusting the weights and biases of the neurons to minimize the difference between the predicted output and the actual output for a given set of input data. This is typically done using a process called backpropagation, which calculates the error at the output layer and propagates it backwards through the network to adjust the weights and biases. Neural networks have been used to solve a wide range of problems, including image and speech recognition, natural language processing, and predictive analytics. They also have been used in various fields such as finance, healthcare, and transportation. Convolutional neural networks (CNNs) are a type of artificial neural network that is commonly used for image and video recognition tasks. They are designed to automatically extract features from images and identify patterns in them. The basic building block of a CNN is a convolutional layer, which applies a set of filters also known as kernels to an input image. Each filter slides over the entire input image, performing a dot product operation at each location. The result of this operation is a feature map, which highlights the presence of specific patterns in the input image. In addition to convolutional layers, CNNs typically include pooling layers, which reduce the spatial dimensions of the feature maps by performing operations such as max pooling or average pooling. This helps to reduce the computational complexity of the network and make it more efficient. CNNs also typically include one or more fully connected layers at the end of the network, which use the features extracted by the convolutional and pooling layers to make predictions about the input image. These layers are similar to those found in traditional neural networks and can be trained using backpropagation. CNNs have been used in a wide range of applications including image classification, object detection, and facial recognition. They have proven to be very effective at these tasks and are now considered to be the state-of-the-art approach for many computer vision problems. Recurrent neural networks are a type of neural network architecture designed to handle sequential data, such as time series data or natural language. Unlike traditional feed-forward neural networks, which process inputs in a fixed order, RNNs allow for information to be passed from one step in the sequence to the next. This makes them well suited for tasks like language modeling, speech recognition, and machine translation. RNNs are characterized by their ability to maintain a hidden state that captures information about previous inputs in the sequence. This hidden state is updated at each step in the sequence and can be thought of as a memory that allows the network to remember previous inputs. The current input and the previous hidden state are combined to produce a new hidden state, which is then used to make a prediction or generate output. One common variant of RNNs is the long short-term memory network, which is designed to address the problem of vanishing gradients that can occur in traditional RNNs. LSTMs use a gating mechanism to control the flow of information through the network, allowing it to selectively remember or forget information from previous steps in the sequence. Another variant of RNNs is the gated recurrent unit, which is similar to LSTMs but has a simpler architecture with fewer parameters. Overall, RNNs are a powerful tool for handling sequential data and have been used in a wide range of applications in natural language processing, speech recognition, and other areas of machine learning. Autoencoders are a type of neural network that is used for unsupervised learning, meaning that they don't require labeled data to learn from. They are commonly used for data compression, image denoising, and dimensionality reduction. The basic idea behind an autoencoder is to have an encoder network that takes in an input and a decoder network that outputs a reconstruction of the input. The encoder compresses the input into a lower dimensional representation, and the decoder attempts to reconstruct the original input from this compressed representation. The goal is to minimize the difference between the input and the reconstructed output, which is typically measured using a loss function like mean squared error. Autoencoders are often used for dimensionality reduction, where the encoder network is trained to extract the most important features of the input data, and the decoder network is used to reconstruct the original data from this compressed representation. This can be useful for tasks like image compression, where the compressed representation takes up less storage space than the original image. Autoencoders can also be used for image denoising, where the encoder network is trained to extract the underlying structure of an image, and the decoder network is used to reconstruct a clean version of the image from this representation. Overall, autoencoders are a powerful tool for unsupervised learning and have a wide range of applications in machine learning and data science. Generative adversarial networks or GANs are a type of machine learning model that are used to generate new data that is similar to a given dataset. GANs are made up of two different models, a generator and a discriminator. The generator is responsible for creating new data that is similar to the input data, while the discriminator is responsible for determining whether the input data is real or generated. The generator and discriminator are trained together in a game-like fashion, where the generator tries to create more realistic data to fool the discriminator, and the discriminator tries to correctly identify which data is real and which is generated. The training process of GANs involves iteratively updating the generator and discriminator models until the generator can create realistic data that is indistinguishable from the input data. GANs have been used to generate realistic images, music, and even text. One of the key advantages of GANs is their ability to generate new data without any explicit knowledge of the underlying structure or rules of the input data. However, GANs can be challenging to train and require careful tuning of hyperparameters to achieve good results. Additionally, GANs can suffer from mode collapse, where the generator produces limited variations of the input data instead of generating a diverse set of new data. That's it for this chapter. I will see you in the next chapter. If you like my content, then please like, share, and subscribe. Thank you for watching.